All right. What we have done so far in Newton's laws. Newton's first law. Is that totally clear? Yes, Patrick, go ahead.
Every object will stay in the same state of motion unless acted on by an outside unbalanced force.
That is true. And can you give one example of illustrating Newton's first law? Just one example. Whatever you said just now.
If the net force is zero, then the velocity will be zero.
Yeah, give an example. That's true. If the net force,
coffee cup right there.
yes. What about it?
It's obeying Newton's first law because it's at motion and no outside forces are acting on it currently.
It's in motion.
Oh wait, no, I'm saying it's not in motion.
It's not in motion because.
No outside forces.
So are there no outside forces acting on it?
Well, I mean,
The table and gravity.
Yeah, the table and gravity are.
oh, they're not in balance.
They are balanced. They're not unbalanced.
What about like, for example, do you see the tissue box right there? Well, do you see how that valve thing is pushing down on the tissue
That's
box?
also a force.
But it's balanced.
It's balanced.
That's why it's thin.
Mm-hmm. So for that tissue box right now, if I have to draw the diagram of the tissue box, let's say the tissue box weighs 2 newtons,
Okay.
and the tap is pushing it down with 1 newton.
Okay. Then the force from the table is 3 newtons?
Exactly.
Oh, now that makes sense.
You got it?
I see what you're saying.
Yeah. Now it's balanced. Now if this push was not there, it would have been just 2 newtons push. But now since the tap is kind of pushing it down, the table has to do extra.
That's pretty cool.
Yeah, that's right. So if it is a balanced system, the object can either be at rest or moving at a.
constant velocity.
That's the first law. And then after that we did the third law, which says for every action, and they should be equal, opposite,
Different times.
acting on different bodies.
Pairs.
Yeah, but we are looking at the qualities of the pairs. They must be of the same
kind of force,
force,
same direction.
same line of action, same time of action. Same time they should be
Same
acting,
line of direction.
and same line of action. Okay? But the most important ones are the first ones we said. Those are, everything is important basically, but if you see that all these points are taken care of, then Newton's third law of pair is properly defined. So Newton's third law simply says for every action there's an equal and opposite reaction. Forces don't come alone, they come always in pairs. And so the challenge is basically you have to identify which is the right pair. Got it? Then we did the second law. What is the second law's main idea? Main idea of the second law?
Force is proportional to acceleration.
When the net force exists, if there is a net force existing, in other words, if it is not balanced anymore, if it is unbalanced, then, all right, if it is unbalanced,
The velocity will change.
the velocity will change. In other words, it should accelerate. And that is what is given by that equation. Net force is equal to ma. So that is our only equation for the second law. The first law doesn't have really a big equation. The first law's equation is net force is 0. The second law's equation is net force is ma. What do you mean by net force?
Total?
Total, the resultant. Okay, the resultant force or total force. That is the net force. So, and third law doesn't have an equation at all. It simply says action-reaction pairs. Correct? All right. Now, we saw in that exercise, we saw how this equation was applied to different situations. So, if you have an object, it will be acted on by some forces. Now, what are the different kinds of forces? That's what we're going to discuss now. Kinds of forces. The first of its kind is weight. What is weight? Weight is a gravitational force on an object by the earth or any other mass. It doesn't have to be from the earth. It can be on by any other mass. So gravitational force is basically the weight. So weight is a gravitational force. Since it's a force, we can write it by using this equation, right? Since F is equal to ma, you can write weight also the same way. Weight is equal to mass times. So it is mass times, but not just acceleration, but we are going to specially write acceleration due to gravity because it's a gravitational force. So what is weight? Weight is mass times gravity. Weight is measured in newtons. Mass is measured in kilograms. What is the acceleration gravity measured in? Meters per second squared. So you can see where Newton is coming from. Newton is kilogram meters per second squared. Right? Any questions on this? So is weight the same as mass? No, not at all. Weight is totally different from mass. Mass is the quantity of, the amount of substance, amount of matter. That is what mass is. It's measured only in kilograms. Weight is a kind of force. Now, since we are on the earth, we are talking about the earth pulling us down. But what force is earth pulling us down? That is called the weight. Jackson, what's your weight?
175 pounds.
No, that's not your weight.
Uh,
What's your weight? What you said is just mass. So what do you have to do now?
Negative 9.1.
Now what you have to do now is
fat on camera.
no, it's okay. It's very common understanding that goes on everywhere. Weight can be easily misunderstood as mass. So even though I asked him his weight, he was actually saying the mass, because that's how we commonly use that term.
Yeah, when you go to
So
the
it's
doctor,
not his fault.
they don't say what is your mass, they say what is your weight.
Where?
When you go to the doctor.
Yeah, that's what I tried once. When the nurse was actually asking me like, what's your weight? And I said 800 pounds. No, not pounds, 800 newtons. 800 newtons. And she was like, 800 what? I said 800 newtons. And then she remembered her physics immediately, and then she said, oh, okay, what's your mass? Okay. I said, all right, now I'll tell her the actual. So what is your pound quantity?
175.
So when it is 175, how do you change it to kilograms? Because pound is not something we use. So divide this with 2.2, and that will get you in kilograms. Can you do it?
79.
79 kilograms.
79 kgs.
When it is 79 kilograms, that's a mass. Now let's find out the weight. Weight is equal to mass times gravity. So 79 times 9.8. You don't have to use a minus sign there, because weight is downward. How much is this?
779.5.
So it's like 780 newtons. So the next time somebody asks you what's your weight, you say 780 newtons.
I will.
All right, that's the right answer for the
Question.
question. And so this is weight, because it is something to do with gravity. Now, do you weigh the same on the moon?
No.
No. On the moon, the acceleration due to gravity is only 1/6 of that of the Earth, approximately. So 1/6 of 9.8 is almost like that. So therefore, your weight on the moon will be 1/6 lesser than what this is. So if it is 78, it's going to be 1/6 of that. 780 becomes 1/6 of 780, which is what, 100? No, yeah. 780 divided by 6. So 130 newtons on the moon, and on different planets is different. So weight depends on factors like, where are you? Are you on Mars? Are you on the moon? Where it is? Okay, that's what the weight depends on. What about mass? What's the mass on the moon?
Mass.
What is your mass on the moon? The same, no difference.
Oh, called them.
Mass never changes. Mass is the same. It is the amount of matter in your body that never changes wherever you are. So mass is independent of the gravitational forces and all that. So he is 79 kilograms. That's it. Whether he is in space or whether he is on the moon or on the earth, he is going to be always 79 kilograms. When you multiply by 9.81, then it will tell you the weight on the surface of the earth only. It's not the same everywhere on the earth. On the earth, it's not the same everywhere. Here, in this place, it is 9.81. That's why we use that number. Now, it's not the same everywhere on the earth because earth is not, it's like flat on both sides and then kind of bulged like that. So earth is something like this. It's more flat at the bottoms and it is bulged out like this.
I thought the earth was flat.
So what happens is if you are on the equator, this is the equator. If you are on the equator, you are further away from the center of the earth. Can you see that? But if you are on the poles, you are closer to the center of the earth. Which means you will weigh
More.
where?
At the pole.
At the poles. You should be weighing more. I exaggerated this a little bit more, but yeah, the factor is the distance makes a big difference. So since if you're at the poles, you should be weighing a little more. Not too much difference, but yeah.
So the Earth's like not like a sphere, like
No.
everyone thinks.
No. Earth is not a sphere. It's more flat on the top and bottom, and it's bulged out on the side. It's like if you spin a ball so fast, it'll like squeezes it from the top. Right?
What? Is
If
that,
a ball spins really fast, I think maybe a baseball, if you hit it maybe at an angle so it kind of spins like crazy, you'll see it like changes to that shape. Yeah.
So, like, for your weight, would the most accurate rate, like, reading on it on Earth be like a 45-degree angle?
I mean, there's nothing accurate. Like, it depends on where you are. So, if you're here on the equator, we used to use for calculations 9.78, not 9.81. Because where I was, it was close to the equator. So it was only a 9.78, maximum 9.8. But we are somewhere here. And so definitely we are closer. So as you go like that, you get closer to the pole, closer and closer. So that's why the gravity changes according to where you are. And that is not only one factor, the other factor is the spinning action. If someone is on the equator, they are spinning fastest. Correct? Isn't there, aren't they going fast? Because after 24 hours, they have to come back to the same spot. So imagine I'm telling you, right, run right away. Go around the earth and come back here after 24 hours. That's what we are doing right now. We are taken for a ride, basically. So we are all traveling right now at a speed which is much more than speed of sound. Why? Because then only you can go all around the earth and come back on time. Well, we are not spinning too much. We are here. So we are spinning lesser. Look. We are making smaller, we are not traveling too much of a distance compared to those who are on the equator. So since the earth is spinning, isn't there an action to be, detached? There's a little pulling out effect. When something spins, like dirt on your bicycle and all that will like get thrown away. So there's a tendency to fly away. If it is not sticking properly, it just jumps off. So we are standing on the earth and the earth is spinning. If there is a certain, if the earth is really spinning fast, we can be thrown away.
that would never happen. Right?
Oh, well, the earth is not going to change its speed like that because the earth is massive, earth has inertia, and so the earth is not going to suddenly, change its motion. Which law of Newton?
One.
First, yeah.
Objects in motion stay in motion.
Yeah, the inertia concept.
What would be the unbalanced force that could possibly act on the Earth? Like some type of meteor?
Some other, no, not a small meteor.
But like one of the,
big ones.
I don't know what they're called.
Be like
Mr.
me.
Francis was talking
The
about
Earth.
that, like we're
Yeah.
right at one of those hitting us, and literally the Earth could like.
I know. I mean, if something really targets the Earth, if something comes and falls, if it is something that is as massive as the Earth, it can even change the direction of motion altogether, and it can mess things up. It can throw us out of the actual orbit that we are in right now.
Well, it hasn't
So
happened.
instead of a year being 365 days, it can be totally changed to some of the. You know what I'm saying?
It hasn't happened in 2020.
And also the day, now if the Earth stops spinning, if you imagine the impact is like that, the Earth kind of stops spinning, then, well, we won't be there to think about it, but I'm just saying, if the impact is so big that it stops spinning, no chance of survival after that. Anyway,
What would happen to us?
yep.
Long.
No, I mean, like, it's going to be a big landslide and big, big meltdown, basically. So therefore,
Dude, quick
what if
death
you're on
or
a
like
plane?
a long death?
Is
Yeah, what
that-
happens if you're on a plane flying?
that plane is also part of the Earth.
Yeah, you gotta agree.
You are almost like on the ground. It's just the sky. Sky is what? Atmosphere is also going with us.
So what
So
if
you're
you're like,
toast.
what if you're on like the space station, like the International Space Station? You wouldn't.
What if you're in an anti-gravity
That's fine.
machine?
Oh wow, so they're gonna take all the, whenever they know a giant meteor is coming across the Earth, they're gonna take all the rich
What if
people
you're-
and the president and
what if
fly
I'm
them to the
Hans?
International Space Station.
But what if the Earth?
What is the point? No return.
What if the Earth?
Where are you going to return to? Yeah.
If the Earth just stops suddenly, we all get thrown off.
Yeah. If the Earth all of a sudden stops, for example, just thinking, while if the Earth suddenly stops because we are going at a speed of sound, it is really fast. Really fast, as fast as F-18s or something like that. We are trying to, going really fast. And so if you're going that fast and Earth suddenly stops, we will be like flying off like a projectile motion. We will come back to the Earth because, imagine an F-18 is flying and suddenly it lost its engine. It's just going to come back, right? Just like that. We'll be tossed, not only we, buildings, everything, including everything together will be like tossed. And that means like you're going to roll over so many things. So that's why I said there's no chance of anything. Everything is going to roll into a pile of dirt, basically. Yeah, so survival becomes difficult there. Yeah, including even if you're thinking about the atmosphere also going to do the same thing. So if there's a plane up there, and the atmosphere is also going to have the same effect. So it's going to toss everything, which means you lose everything out. Yes,
Wouldn't you be safe on the pole since you said it wasn't spinning as fast?
that's true.
So you could
You would be
be
safe.
On the poles, absolute. So what's going to happen to a person standing right there? Now he's not spinning at all. He's just doing this, like this. At this time, he's like this. And in 24 hours, he's spinning like that and coming back to the same spot. So he's not traveling a distance. Can you see? Over here, they are traveling that distance.
Who lives there?
That's Arctic and Antarctic, yeah.
That's like nobody lives there.
No.
Santa Claus.
Polar bears and penguins, they live in different places, right?
Santa Claus.
One penguin would be alright.
Santa Claus.
Where do penguins live? Antarctica, right?
Yeah.
And Arctic is for the.
Oh, and like in very bottom of like
And the little
there's like they're in weird places too, like Australia and like
Yeah, there are some here and there, but
I think
most
there's
of
some in like South America too, like in the Patagonia.
because it's almost close to there. South America is almost like there.
Yeah.
So,
That's pretty cold.
So
Cold?
far.
Isn't it?
South America,
Very south. It's the tip of South America. The weather is extremely hard.
possible.
The white-
All right, let's get back. So you know the difference between weight and mass clearly. What if you are right in the middle of the Earth?
You're dead.
What's your weight?
Zero.
Zero. You are right in the middle of the Earth, in the center of the Earth, which means what? The Earth is all around you, and so this part of the Earth is going to pull you that way. This part of the Earth is going to pull you that way. This part of the Earth is going to it's kind of pull on all sides. So you are sitting with the net force of zero. So you're not going anywhere. So that's a place where G is zero. Okay, so no acceleration due to gravity here because it's all balanced. Now if you're outside here, it's 9.81, 9.8, whatever. And if you go further away, it comes down because your distance is increasing. So as you go further and further away, the distance increases, so the gravity also comes down. So the weight is something that changes according to the place. So he's 780 newtons, but his mass is 79 always. Newton weight, this is different.
So wait, like theoretically, if you dug to the center of the Earth, would you be weightless like you were in space, just like floating around?
It'll be.
Well, I know you'd be
Excluding, dude, burn.
I mean,
Excluding the law there. So
I know you'd be dead, but like besides all that, like would you just be floating around?
you wouldn't know because you'd be dead.
I mean, if you think of digging 4,000 miles and going all the way down here,
Is that all it is 4,000 miles?
Yeah.
4,000?
4,000 miles, and
I mean-
another 4,000 miles here on the other side.
From here to California is like 2,000 miles, isn't it?
Yes.
Yes, possibly.
So that's just
Two
California and
continents.
back.
Through the
But you're digging.
core of the band.
Let's take it to China.
You're not flying or driving, you're digging. And of course, as he said, the other impacts, the temperatures and all those, over here is still molten. So it's not something that you can reach there, So it's going to be really hot inside here. So thinking of going down there, theoretically, yes. If you can actually make a tunnel going all the way down there, at this point is zero gravity. Now, think of it, if you can build a tunnel like this, then going from here to China will be an easy job. Just jump into the tunnel. And you'll be there after 1 hour or something like that.
What? Wait, say that again?
Yeah, the time-wise, it's only that much.
Yeah, hold on. How would that work? Because then first you're going down.
You're accelerating,
Then you're falling up the.
then you're decelerating.
So you're, oh god, that's crazy.
Here you are actually at rest, but you're accelerating speed faster, and here's the fastest. And then after that you start slowing down. Look at this marker. When I throw it, isn't it slowing down and stopping? That's exactly what happens from here to here.
So you're gonna shoot up out of the tunnel?
No, you'll just barely reach there. Just climb over.
But you'd be feet.
What if you fall back?
Because if you jump in, like if you.
I mean, no. Jumping is totally an impractical. It's not practical at all. What I'm talking about is if you have a tunnel, if the tunnel is evacuated, like vacuum, no air, nothing to oppose you. If it is evacuated, so basically think of an evacuated tube, and then you are put into a capsule, and then the capsule is left inside. So what will happen to that capsule? No air resistance, nothing. So it's just the weight of the thing. So it will go down, and then it will be fastest here, and then it will just reach there on that side, and then somehow stop it when you reach there.
What happens if you want to go back? Do you accelerate still, or is it like reverse?
Yeah, it will be accelerating. So if nobody catches you there, you'll just come back again, look up here, and go down again. This is what is happening.
Pendulum.
Look at this, like a pendulum. See what's happening here is you release it from here. That's why it's fast here. It's fastest here. And from here to here it slows down and stops. And from here, if nobody catches here, then it's going to repeat the cycle. So right now what's happening is the fastest here, and these 2 points it's stopping. It's literally stopping there. But since I'm not holding it there, it just goes back.
Will that continue infinitely if there was like in a?
If there's no resistance and all that, it's supposed to go infinitely. Yes.
Have they ever? Oh well, yeah.
No, they haven't.
You know how you?
Now in the AP
you
classes-
said there's things where they make where there's no.
In the
air.
AP classes, students will actually end up finding out how long it takes to go to the other side. They will use the calculations and get exact numbers. If this is possible, how much time it takes. That's why I said I think it's approximately 1 hour. No. That's not even 1 hour. Less. 20 minutes, 21 minutes. You reach China in 21 minutes. Any questions about weight? Weight and mass. Don't get mixed up with the weight and mass. Alright. Now I'm going to give you a problem. I want your answers. Here's the problem. An object of weight 20 newtons is pushed with a force of 10 newtons, what is the acceleration? A 20 Newton object is pushed with the force of 10 newtons, what is the acceleration? So what I told you is I didn't give you the mass of the object. Look at this. That's not the mass of the object. I gave you the weight of the object. So what you need to do is use the equation weight is equal to mass times gravity and pull out the mass of this. We don't know the mass. That's your first job. Because you can't apply F is equal to ma unless you know the mass. So 20 Newton object. So find the mass first. And then use the F is equal to ma. Good. So mass comes out what? 2.04?
Yes.
So the mass comes out 2.04. And now you know the mass. You can apply net force is equal to mass times acceleration. And 2.04 times acceleration is 10 newtons that you're applying. And therefore you get acceleration as 4 point something, right?
Yes. 4.9.
Make sense?
Makes sense.
So if you're given something like this, don't just blindly take anything that's given as mass and go on. This is not mass. Look at the unit. The best thing to do is look at the units. You may be confused by the word weight, but look at the units, and that's not the unit of mass. It's kilograms. So change the newtons to kilograms doing this. Okay? Questions here? So weight is one of the kind of forces. The other kinds of forces are tension. What is tension? Tension is a force in a string, rope, cable, etc. You know, it can be in a string, in a rope, in a cable, in a wire, in a lanyard, anything, due to stretching. If you try to pull something, then look at this lanyard. Watch what I'm doing here. I'm pulling this ring. Why is my hand not going? I'm applying a force, but my hand is not going. What is this doing?
Stretching.
Because I ended up stretching it, this is developing a tension. You can see the tension right there. This is developing a force inside itself, which is stopping me. So right now, I'm pulling it, this is pulling me back. And that pulling back is called the tension. So right now, look at this. Is there a force acting on the key? Which is the weight, right? Yeah. mg. Yeah, mg is acting downwards. But is it going down? It's not going down. What is stopping it? Tension. Clear?
Isn't there tolerance on tension?
There is a
the
tolerance
amount
on tension. You
where it
can't
would
go.
break?
Yeah, the tension cannot exceed more than a certain amount. So once you cross that limit, then it breaks. So why something should break is because it is not able to hold on to that number, value. And therefore, it breaks after that. Okay? So that's called tension. And in a string, that's what you do. So if you're going to mark, if this is an object of mass m, what are the forces acting on this? When like that. What are the forces acting on this? Gravity is pulling down. What do you write here?
Negative.
Just write mg, because that's a weight. It's always good to write down just that term, weight. No, you can also write w if you want, which is also weight, but it will be better to write mg as a weight. What is acting upward? Tension. Tension is pulling it up. Make sense? So tension is a force that will be required. The other kind of force is called normal reaction. Normal reaction. The word normal means perpendicular. The word normal stands for perpendicular. So it's a perpendicular force on object by surface. That is called normal reaction. It's a perpendicular force offered by the surface on the object. That's called normal reaction. So, if this is a book that is sitting here, what's a book trying to do to the table? What is a book trying to do to the table? Push it down. So, what is the table doing?
Pushing it out.
And that is a normal reaction. That is a normal force, normal reaction. Some books use NR for normal reaction. Some books use FN for normal force, normal reaction. So doesn't matter what equation is used, what term is used, NR or FN. That's called the normal force. Now watch this. I'm putting my hand on the board. I'm resting there. Which way is a normal reaction? By the board on me, straight out, not along my hands. Because what is normal?
Perpendicular.
So it's perpendicular to the surface. Look at this. This object is sitting there. It's sitting there, but it's not like on a horizontal surface or on an inclined surface. Which way is the normal force offered by the book on that object?
Sideways. Kind of.
It's like that.
Yeah, like that.
Perpendicular to surface. That's what you should be thinking. It's perpendicular to the surface. Is that clear? Normal reaction part of it? Good. So normal reaction is a force that's acting perpendicular on the object, and it acts on the object. And they're all measured in newtons. The next force is friction. Friction is a force that opposes motion.
Is this the last one?
Kind of. Friction is a force that opposes the motion. Now it's pretty easy to say friction is a force that opposes a motion, but it's a very important topic. Friction itself is a very important topic. It's a force that opposes motion. Friction is different types. There's a fluid friction, and there's a solid friction. There is something called fluid friction. What's a fluid? Anything that flows. Air is a fluid. Water is a fluid. So fluid friction and solid friction, what is the main difference between them? Solid friction is between two solid surfaces, like me rubbing my hands like that. That is solid friction. Two solid surfaces. And what's fluid friction? It is two fluid layers. One layer of air with another layer of air. Or one layer of water with another layer of water. Two layers rubbing against each other of a fluid. That's called fluid friction. Now the common fluid, now thinking about fluid themselves rubbing against each other is pretty difficult to understand, right? That's why let me explain to you this way. Think of your car. Is there a layer of air stuck with your car? Stuck.
Yes.
Yes. So there is a layer of air stuck with your car. So your car is bordered by a layer of air, which belongs to the car, basically, because it's stuck those atoms of the air are stuck with the atoms of the body of the car. Make sense? So there's a layer of air surrounding your car, which belongs to the car. If you drive your car, it goes with you. Now, when you start moving, there are other layers outside, which are not going to go with your car. So what happens is the layer that is stuck with your car is rubbing against the other layers. You see that? And that's what we call as drag forces. Air resistance. Air resistance is simply that.
Okay, so I guess it's fun that I was watching the Tour de France and there's a rule that like you can't have your bike behind team cars for a certain amount of time. Is that kind of the reason why? Because drag forces, they try to get slipstream of the back of the car.
You're talking about big trucks or something?
Dirt
Dirt
bikes, yeah. But these are people on bikes.
You can't keep what? Again, say that again?
You can't keep your bike behind the car for a certain amount of time. Are you sure? Like they move their bike right behind the car.
Okay. There are multiple reasons there, and you will see them as we go on. There is a Bernoulli's effect. That is another major issue that can cause accidents even. So that is one factor which is mainly because of pressure differences. But what we are focused right now here is just talking about the air resistance part. Only the air resistance.
Isn't the air you're talking about that is a fluid force that's touching your car? What is it whenever there's a fluid touching a solid? What is that friction called?
Fluid touching a solid.
Yeah, like
Fluid
that-
is basically in contact with the solid.
right.
So is there a layer of air stuck with this marker?
right. What's that friction? That's what I'm talking
There's no
about.
friction. It's stuck with it.
Oh, it's just like
It's stuck with it.
oh.
It's atomic bonding. Now, when I move this pen, when I move this marker, there are stationary layers of air that I'm rubbing against. That's called fluid friction. So, an example is air resistance. What does this depend on? Air resistance depends on what factors? Let's find
The
out.
size of the object that the air is connected to.
So, in other words, area.
yeah, area.
It depends on area. Depends on area. What else? It depends on speed. If you go faster, it's going to drag you more. If you're not moving at all, will it drag you? No.
What about temperature?
Temperature might affect the nature of the fluid itself, but otherwise not a big deal. Shape also matters. Shape will be taking care of the area. Shape is important too. So yeah, aerodynamic, if it is more aerodynamic, it's easier to slide through, right? So that is fluid friction, depends on area, depends on speed, depends on the fluid itself. Like, are you talking about water or air or oil or, right? Depends on these things. Solid friction, what does it depend on?
The objects.
First of all, the nature of solid. Like, are you talking about this table with this book, or you're talking about rubber tires with the road? That one. That is the nature of the solid. So, two smooth surfaces, that will be different. What is the other thing that it depends on? It only depends on one more thing. It does not depend on area. Like this book. The way I drag it like this or like this, it doesn't matter. Friction is not affected by area or by speed.
What about the shape? The shape.
Nothing. Only two factors. One is the nature, what kind of solid you're talking about. The other one is the normal force. The normal reaction.
The weight.
No, normal reaction. Not weight. It's not the weight. Look at my hands. My hand has a weight, right? I put it on the table. I'm putting my hand on the table and I'm sliding my hand. Am I experiencing some friction?
Yes.
Yes. Watch what I'm doing now. I'm experiencing right now some friction. Now my hand is not changed, but now I experience a lot of friction. Why? What happened in the second case? I pushed it more, so the table pushed me more. So that's the thing that changed.
Gotcha.
Only those two. Now, which way is friction when I walk that way? Tell me.
That's the opposite direction.
When I'm walking, which way is friction on my feet?
Opposite direction.
It is that way. What helps you walk is friction. You see, your action of walking is this. You're dragging the ground backward and you're using that grip to go forward. So what helps you walk forward is, that's why on a black ice you're not able to walk. Why? Because you're trying to like grip it. Nope, I'm not getting the grip. And so you can't move from there. So what helps you walk is friction. What makes your car go forward? Friction.
So
Don't
that
say
was the
wheels.
question the other day whenever you said no, it wasn't the wheels.
Exactly. No wheels, no steering wheel, engine, nothing. Friction is what takes your car forward. Imagine your car is sitting on ice. No matter what you do, how good your car is, it's not going to move from there. Coming to solid friction again. Solid friction is two types. We learned it. We have static friction and we have kinetic friction. Now, static friction is a friction between surfaces when they are not moving. So static friction can take different numbers. Can static friction be 0? Yes, no?
No.
What's the static friction on the book right now? 0. Then why did you say no? The static friction on the book is 0. Why? Because nobody's attempting to apply a force on it, and therefore there's no need to apply an opposition. You understand what I'm saying? So the book, right now, the static friction is 0. The Fs can change from 0 up to a limit. So that's why I gave you the graph. The friction can grow evenly up to a limit, which is called static friction, limiting value. So when we say static friction, we are talking about the limits, the maximum. How much is the maximum static friction that is actually applied, that can come into existence? We are more concerned about that, not the zeros, not the 1 Newton, 2 Newtons and all that. So these are all there, but what is important to us is that the moment it is about to slip, that's called the limiting value of static friction. We can write it down. Limiting value of static friction. So when you say Fs, we imply that it is a limiting value. As soon as it starts slipping, then the kinetic friction, Fk, comes into play. And you know the Fk is smaller than the static friction. Fk is just one value. It's not growing from 0. Fk is a steady number. Static friction, Fk is kinetic friction, or this is kinetic friction. The kinetic friction is a single number. Whereas static friction can take numbers from 0 to a max. Is that clear? Kinetic friction is just one value. And the static friction can build up to a maximum value of limiting friction, that is, so the Fs, I'm taking this graph off. Okay. So the static friction keeps growing. As we know, what are the factors the static friction depends on? Fs is proportional to what? Did we say some of the things? Yeah. Static friction will involve applied forces and all that, but applied force is what is causing the static friction. But we are trying to find out what is static friction dependent on. Okay, so if you don't apply a force, there's no static friction. That's true. But then we are talking not about any other static friction. We are talking about the maximum, the peak. The moment the objects are going to slip, that friction, like when I push this book, when did it just slip? When I cross that limit, right? That limit is what we are talking about. So therefore we don't apply, we don't worry about applied forces. So what is that limit controlled by?
The normal force of the surface.
The normal force applied by the surface on the object. The normal reaction. Static friction, the limiting value of static friction depends on the normal force, the force applied by the surface on the object. If you're talking about your car, then how much force is the car applying on the surface? That much force the surface is applying on you, on the car, that is a normal reaction. So static friction depends on that. And what else static friction depends on is the nature of surfaces. Nature of surfaces. What is the surface like? Is it glass with glass, glass with rubber, rubber with rubber, concrete with rubber? What kind of surface are we talking about? The book with a table, or book with book? So that is the nature of surfaces. So depending on the nature of surface, it's going to be different. And so F is proportional to NR, and F is equal to a constant of proportionality times NR. You know the constant of proportionality concept, right? If you have a proportional sign, and then if you want to convert it into an equation, we need to bring in a constant, right? And this is what we call as the coefficient of static friction, coefficient of static friction. Coefficient of static friction is this mu s. And what is this? It is the static friction, the limiting value, the peak value. When it is about to slip, when things are about to slip, that is equal to mu s times nr. Mu s is a coefficient of static friction. It has no units. It has no units. It's purely a mostly a number, a decimal value, a fraction. For instance, I'm just giving an example now. When I tried to move this book, when I tried to move the book on the table, let's say the book was 5 kilograms. What is the normal reaction? So before you decide what is normal reaction, find out how much the book is applying on the surface. How much? 9.8 times 5, because 5 kilogram means this book has a weight of 49 newtons. The book has a weight of 49 newtons. The mass of the book is 5 kilograms, the weight of the book is 49 newtons. So when the book has 49 newtons and is sitting on the table is not letting it fall under gravity. That means what is the table applying on the book? 49 newtons. So the normal reaction is 49 newtons. We have seen this before, many examples. So the book wants to go down because of gravity, but the surface is refusing it. How much is the normal reaction? Trying to cancel off that force of gravity, it's 49 newtons. So we know the normal reaction is 49 newtons. All right? Now if I don't apply any force, how much is the frictional force? 0. If I apply 1 newton, it is 1 newton. I apply 2 newtons, it is 2 newtons, it's growing. And let's say it has a limiting value. Suppose the limiting value is this. The moment I applied 15 newtons, it slipped. What does it imply? As soon as I applied 15 newtons, the whole thing slipped off. So what did you understand about the maximum Fs that it could hold on to? How much? 15. The graph is going up. Maximum friction that it could hold on to is how much? 15. And that is, so at 15 it slipped. Implies that the static friction just built up to 15 and after that gave up. So how much is the static friction? 15. So Fs is equal to mu s times normal reaction, substitute. 15 is equal to mu s times 49. So what is mu s? 15 over 49, which in decimals is 0.31. What is 0.31? It is the coefficient of static friction between the book and the table. Make sense? That's the coefficient of static friction between the book and the table. And between the book surface and the table surface, that is a number, whatever be the object. Like if I keep 2 books, doesn't matter, still the same thing applies. If I keep 2 books on each other, how much force can it hold on to? If I keep 2 books, similar books on each other, how much force will this hold on to? What's the limiting value? If I keep 2 similar books, one on top of each other, how much will Fs build up to?
30?
30. Yeah. Static friction, it depends on normal reaction. When you put 2 books on each other, what's the normal reaction? It is now 98. So if it is 98, then this will build up accordingly because a number, this number 0.31 is a fixed number between the book surface and the table surface. It's a fixed number.
Just wanted to clarify, so that's just like the proportion between
Static friction
static friction
and normal reaction.
Okay.
So basically coefficient of static friction is a ratio of the limiting value of friction to the normal reaction. Yeah,
Is it always that way, or is it different depending on what surface you
doesn't matter. It's always like that. The only thing is if I'm going to use this book on glass, I may not be requiring 15 newtons to get it slipped, right? So probably then the coefficient of static friction between the book and the glass is like lower, 0.2, something like that. Now if I'm going to keep this book on ice and then slide it, it'll be requiring the least force to get it started, right? So maybe 1 or 2 newtons will be enough to make it go. So it'll be like 2 newtons divided by 49. So that will be the coefficient of static friction between this surface of the book and the ice. Now if you're talking about one ice block on another ice block, then you can, before it actually like sticks onto each other, if it's going to slide, it's going to be definitely much smaller. So a metal object on ice is definitely going to cause very little friction, especially if it's wet ice. If it's wet ice, a metal object will slide with almost negligible amount of frictional force. Do you get it? And ice skating, the blade which rests on the ice applies a pressure enough to melt the ice at that point, because the pressure changes the melting point. So when you apply a pressure on a particular point on ice, it melts that point. And that's why slipping becomes easier. Make sense? Alright, so coefficient of static friction, is this part of it clear? When you are applying these into problems, then you have to take all these points into consideration when you actually look into a problem. That's why I'm slow on this. Make sure you understand this. So Fs is equal to mu s times normal reaction. It's an important force, important equation. Keep that in mind. Now, coming to kinetic friction. Kinetic friction also depends on normal reaction and it depends also on the nature of surfaces. So we have mu k times nr. The coefficient of kinetic friction between the book and the table will be smaller than mu s. So in our example for static friction, how much was the force needed to get it going? How much was the friction? 15 newtons. But after it starts slipping, if I want to maintain a constant velocity, I need to just apply 10 newtons. See? I need to apply only 10 newtons and it keeps going. That means what is the kinetic friction? It will be 10 newtons. So once the book starts sliding at constant velocity, then you're applying a force this way, but the kinetic frictional force should be equal to what you're applying, right? So if I'm applying only 10 newtons to keep it going at constant velocity, Fk will be 10. I'm just throwing numbers. It doesn't have to be exactly these numbers, yeah.
So it doesn't matter if you're moving at like 80 miles per hour or like 60 miles per hour.
It doesn't matter.
If you apply the same force, it's going to keep
It
going.
is, yeah. I can move it at a constant velocity of 10 meters per second or 2 meters per second. Once it is moving, it is fixed. That's why the line was horizontal. Do you see that line on the graph? Once it starts moving, immediately it becomes a steady line. How fast you go doesn't matter. Alright, so constant velocity. So what's happening here now is Fk is 10. How did you decide Fk was 10? Because I told you I'm applying 10 newtons and it is moving at a constant velocity. So obviously this must be 10. If this was less than 10, it should have. If this was less than 10 when I applied 10, this should have
Accelerate.
accelerated, because 10 and 8 or something like that, you know, it will be accelerating. You understand? If I'm applying 10 and if this is like 12 or something, it will decelerate. From this velocity, it will slow down until it comes to halt. So when it is moving at a constant velocity, it is definitely equal. Okay? So those are some clues that you have to pick up from problems. Because they'll tell you an object is sliding at a constant velocity, boom, over. You got the clue. It's moving at a constant velocity. That means whatever is making it go at a constant velocity is the kinetic friction value. Make sense? I repeat this again. In the problems, they won't tell you clearly what is what. They won't tell you kinetic friction. Instead, they will word it like this. The object is moving at such and such a velocity when this much force is applied. And then they'll ask you further questions. They won't tell you whether there is a kinetic friction existing or not. You should understand it. When they say something is applied and yet it is moving at a constant velocity, what does it mean? It means there is definitely something opposing it, and that opposing force must be the same as the applied force. So that conclusion that you come to during problem solving is a very important thing. All right? It's just not F is equal to ma. The whole chapter is based on F is equal to ma ultimately. But how you apply it is important. How you pick up clues is important. So Fk is proportional to normal reaction, and Fk also depends on the nature of surfaces. Fk does not depend on how fast you are moving. You can write it down. Fk does not depend on how fast you're moving. Alright, you learned enough here. Now let's go to fluid friction and look at some of the concepts of fluid friction. So what is fluid friction? Fluid friction is one fluid layer applying a drag force on the other fluid layer. Alright? It could be actually fluid with fluid, or it could be a fluid layer stuck with an object rubbing against another fluid layer stagnant. Like if you throw a baseball, there's a layer of fluid or air stuck on the baseball, and the baseball is moving against a standing layer of air. So there is a little rubbing there between the two layers, and that is what we call as the air resistance or the drag forces. Now those fluid friction depends on what factors. So what is fluid friction? Again, it is the friction between one fluid layer against the other fluid layer. Let's say your car, there's a fluid layer stuck with your car, and there is stagnant fluid layer on the road. So when you're actually moving, those two fluid layers are rubbing against each other. Factors. What factors? Huh? Nature of fluid?
Sure, yes.
Okay. Nature of fluid. Because when you say surfaces, automatically it means that what kind of surfaces, and therefore nature of fluids. Yeah. Is it air or is it water? Look at here. All right. We are still on this. Nature of fluid. And what's the next factor? Let me give you an example. Pay attention. Imagine there are two people walking in knee-deep water. There's water and two people walking in knee-deep water. One has fat legs. One has fat legs and one has blade-like legs.
Oh, that's me.
Okay? Now, who will find it difficult to walk through that water? The fatter one or the fatter one, obviously. So what is different between them? Surface area. So fluid friction depends on surface area, whereas solid friction was independent of surface area. I discussed that earlier. Solid friction was independent of surface area, right? But here, fluid friction depends on surface area. So how much surface area does your car have? The drag forces will be dependent on that. Okay? Now think of the same two people. So the one with blade-like legs can cut through the water. But this will have more air resistance. Okay? Think of two people with identical kind of legs. Two people with identical surface areas. The one is walking and the other is running. Who has more drag forces? The running one. And that's why if you try to run knee-deep water, you will trip and fall because the top part of the body says go, but the bottom part is being pulled backward. So you end up falling. And if you want to really run in water, what you should do? Lift your legs up, exactly, because air resistance is negligible compared to the fluid resistance. So you some kind of leap. You have to jump out and then make your step. And that way you can actually be faster if you're running in water. If you try to go like that underwater, that's going to be tough. All right? So, depends on what?
Time is like
Depends on relative velocity. It depends on the nature of the fluid. It depends on the surface area. And it depends on the relative velocity. So, you can put all these things together. We are not looking at it into an equation format now because that is beyond the scope. To find out exactly what is the frictional force for an object, we need a constant of proportionality, which is called coefficient of viscosity. But we are not going that far. So right now, understand the factors only. Here, depends on the nature of surface and normal reaction. It does not depend on area, it does not depend on relative velocity. Got it? Whereas over here, it does not depend on normal reaction, but it depends on area and relative velocity, which this one was independent of. So, fluid friction. So, like a truck and the driver's compartment. This is basically what it is, but they have something here like that, a dome. Why they have that dome over there is to reduce the surface area, because what if air is coming and blocking it like that and climbing over? So that's kind of more of a resistance. So this way it streamlines the air better to make it go. That's why your windshield is like that, tilted, not flat. If you have a car with a windshield like that, as it used to be in the past. Why those cars are not going to be good these days is because we have better speeds. And those cars were going only at 10 miles per hour, then it's okay. If you're going at 10 miles per hour, this is not going to be a major issue. But for cars that are going faster, now we have windshields that are going like that. Right? It's like tilted. So the air kind of glides over. So air resistance will be lesser in such cars where you have. So the aerodynamics of your car and all that is a very important factor. So that is fluid friction. Hope you understood all about friction. Now when we apply these things into problems, that's when you should be. Let me give you a simple problem on friction right now before we go ahead. So let's say this is an object, is a mass of 10 kilograms sitting on a surface whose coefficient of static friction is 0.4 and the coefficient of kinetic friction is 0.3. And it's a horizontal surface. And the problem goes like this. The object just begins to slip. The object just begins to slip. when a certain force is applied. The object, you can write it down in words, don't just, the drawing alone is not enough. Okay, draw the diagram. It's a very important thing to draw the diagram because you need to draw forces on the diagram later on. So make a good enough diagram, not a tiny one. What did I say?
An object begins to slip.
Yeah, the object just begins to slip when an applied force, when a force is applied. Find the applied force. And the acceleration of object after slipping. Go. So the answers come out like this. The applied force for it to just slip comes out how much? 39.2 newtons. And what happens after it slips is definitely an acceleration because the force is still 39.2 forward. So the force is still 39.2 forward, but the force backward is now not Fs but Fk. You need to evaluate that Fk now. What is Fk as it starts moving? Fk is going to be 0.3, this constant, times the normal reaction. So the weight is 98, therefore the normal reaction is 98. This one is how much? 29.4 backward. Now you can see that this 10 kilogram object is being acted on by two forces. One is 39.2 forward, and there is a force of opposition of 29.4 backward. Are they balanced forces? And so which law is going to come in now? Second law. The net force is equal to ma. So the net force is equal to ma comes in. Net force is this 39.2 minus 29.4 is equal to ma. And then find out the acceleration. So that will be 9.8 is equal to 10a. So acceleration is 0.98 meters per second squared. So once the object starts slipping, it will slip at that acceleration. Okay? Any questions on this?
Can you just read that up there for a second?
Okay. It's already 2 seconds. We can take a picture if you want, and then fill it up later. So the concept is very clear here. First, understand what's a normal reaction, and then find out how much is the frictional force, and the frictional force comes out exactly 39.2. So that should be the applied force. The frictional force is 0.4 times 98, which is the applied force for it to just get it going. And once it starts moving, then the friction drops to a new value of 29.4, and so the net force is equal to ma, and you just work it out.